So, in this module we will look at supervised learning, right. If you remember in supervised learning we talk about experience, right, where you have some kind of a description of the data. So, in this case let us assume that I have a customer database and I am describing that by two attributes here, age and income. So, I have each customer that comes to my shop, I know the age of the customer and the income level of the customers, right, and my goal is to predict whether the customer will buy a computer or not buy a computer, right. So, I have this kind of labeled data that is given to me for building a classifier, right. Remember we talked about classification where the output is a discrete value, in this case it is yes or no. Yes is the person will buy a computer, no the person will not buy a computer, and the way I describe the input is through a set of attributes. In this case we are looking at age and income as the attributes that describe the customer, right. And so now the goal is to come up with a function, right, come up with a mapping that will take the age and income as the input and it will give you an output that says the person will buy the computer or not buy the computer. So, there are many different ways in which you can create this function, and given that we are actually looking at a geometric interpretation of the data, I am looking at data as points in space, one of the most natural ways of thinking about defining this function is by drawing lines or curves on the input space, right. So, here is one possible example. So, here I have drawn a line and everything to the left of the line, right, these are points that are red, right. So, everything to the left of the line would be classified as will not buy a computer, and everything to the right of the line where predominantly the data points are blue will be classified as will buy a computer. So, how would the function look like? It will look like something like, if the income of a person, remember that the x axis is income and the y axis is age. So, in this case it basically says that if the income of the person is less than some value, right, less than some x, then the person will not buy a computer. If the income is greater than x, the person will buy a computer. So, that is a kind of a simple function that we will define. Just notice that we have completely ignored one of the variables here, which is age. So, we are just going by income. If the income is less than some x, then the person will not buy a computer. If the income is greater than x, the person will buy a computer. So, is this a good rule? More or less, right. I mean, we get most of the points correct, right, except a few, right. So, it looks like yeah, we can survive with this rule, right. So, this is not too bad, right, but then you can do slightly better, right. So, now we got those two red points, that those pesky red points which were on the wrong side of the line earlier now seem to be on the right side, right. So, everything to the left of this line will not buy a computer, everything to the right will buy a computer, right. Everyone who is to the right will buy a computer. So, if you think about it, what has happened here? So, we have improved our performance measure, right. So, at the cost of something. So, what is the cost here? So, earlier we were only paying attention to the income, right, but now we have to pay attention to the age as well, right. So, the older you are, right, so the income threshold at which you will buy a computer is higher, right. So, the younger you are, younger means lower on the y axis. So, the younger you are, the income threshold at which you will buy a computer is lower, right. So, is that clear? So, the older you are, right, so the income threshold is shifted to the right here, right. So, the older you are, so you need to have a higher income before you buy a computer, and the younger you are, your income threshold is lower. So, you do not mind buying a computer even if your income is slightly lesser, right. So, now we have to start paying attention to the age, right, but then the advantage is you get much better performance, right. Can you do better than this? Yes? Okay, now almost everything is correct except that one pesky red point, but everything else is correct. And so, what has happened here? We get much better performance, but at the cost of having a more complex classifier, right. So, earlier if you thought about it, in geometric terms, so first you had a line that was parallel to the y axis, therefore I just needed to define a intercept on the x axis, right. So, if x is less than some value, then it was one class, if it is greater than some value, it was another class. So, in the second function, it was actually a slanting line like that. So, I needed to define both an intercept and a slope, right. And now here it is now a quadratic, so I have to define 3 parameters, right. So, I have to define something like ax squared plus bx plus c. So, I have to define the a, b, c, the 3 parameters in order to define the quadratic, and I am getting better performance. So, can we do better than this? Okay. This somehow does not seem right, correct? Seems to be too complex a function just to be getting this one point there, right. And I am not sure, I am not even sure how many parameters you need for drawing that, because Microsoft used some kind of spline, PowerPoint used some kind of spline interpolation to draw this curve. I am pretty sure that it has got lot more parameters than it is worth. And another thing to note here is that that particular red point that you see is actually surrounded by a sea of blue, right. So, it is quite likely that there was some glitch there, either the person actually bought a computer and we have not recorded it as having bought a computer, or there was some extraneous reason. The person comes into the shop sure that he is going to buy a computer, but then gets a phone call saying that there is some emergency, please come out immediately, and therefore he left without buying a computer, right. There could be a variety of reasons for why that noise occurred, and this will probably be the more appropriate classifier, right. So, these are the kinds of issues that you will have to think about. What is the complexity of the classifier that I would like to have, right, versus the accuracy of the classifier. So, how good is the classifier in actually recovering the right input output map, and are there noise data in the input, in the experience that I am getting, is it clean or is there noise in it, and if so, how do I handle that noise, right. So, these are the kinds of issues that you will have to look at, right. So, so these kinds of lines that we drew, right, kind of hiding one assumption that we are making, right. So, the thing is, the data that comes to me comes as discrete points in the space, right, and from these discrete points in the space, I need to generalize and be able to say something about the entire state space, right. So, I do not care where the data point is on the x and y axis, right, I should be able to give a label to that, right. If I do not have some kind of assumption about these lines, right, and if I do not have some kind of assumptions about these lines, the only thing I can do is, if the same customer comes again, right, or somebody who has exact same age and income as that customer comes again, I can tell you whether the person is going to buy a computer or not buy a computer, but I will not be able to tell you about anything else outside of the experience, right. So, the assumption we made is everything to the left of a line is going to do one thing or the other, right. So, everything to the left of the line will not buy the computer, everything to the right or everyone to the right will buy a computer. This is an assumption I made. So, the assumption was the lines are able to segregate people who buy from people who do not buy, or lines or the curves are able to segregate people who will buy from who will not buy. So, that is a kind of an assumption I made about the distribution of the input data and the class labels, right. So, this kind of assumptions that we make about these lines are known as inductive biases. In general, inductive bias has like two different categories. One is called language bias, which is essentially the type of lines that I am going to draw. Am I going to draw straight lines, or am I going to draw curves, and what order polynomials am I going to look at, and so on and so forth. These form my language bias. And search bias is the other form of inductive bias that tells me how, in what order am I going to examine all these possible lines, right. So, that gives me the gives me a search bias, right. So, putting these things together, we are able to generalize from a few training points to the entire space of inputs, right. So, I will make this more formal as we go on in the next set of modules, right. And so, here is one way of looking at the whole process. So, I am going to be giving you a set of data which we will call the training set. So, the training set will consist of say as an input which we will call as x and an output which we call as y, right. So, I am going to have a set of inputs. I have x1, x2, x3, x4. Likewise, I will have y1, y2, y3, y4, and this data is fed into a training. This data is fed into a training algorithm, right. And so, the data is going to look like this in our case, right. So, remember our x's are the input variables, right. X's are the inputs. So, in this case I should have the income and the age. So, x1 is like 30,025 and x2 is like 80,045 and so on and so forth, and the y's are the labels, they correspond to the colors in the previous picture, right. So, y1 does not buy a computer, y2 buys a computer and so on and so forth. So, this essentially gives me the color coding. So, y1 is essentially red and y2 is blue, right. And I really, if I am going to use something numeric, right, this is what we will be doing later on, I really cannot be using these values. First of all, y's are not numeric and the x's vary too much, right. So, the first coordinate in the x is like 30,000 and 80,000 and so on and so forth, and the second coordinate is like 25 and 45. So, that is a lot smaller in magnitude. So, these will lead to some kind of numerical instabilities. So, what we will typically end up doing is normalizing these so that they form approximately in the same range. So, you can see that I have tried to normalize these x values between 0 and 1, right. So, I have chosen an income level of say 2 lakhs as the maximum and age of 100, and you can see the normalized values. And likewise for buys and not buys, I have taken not buys as -1 and buys a computer as +1. These are arbitrary choices now, but later on you will see that there are specific reasons for wanting to choose this encoding in this way, right. And then the training algorithm chugs over this data, right, and it will produce a classifier. So, now this classifier I do not know whether it is good or bad, right. So, we had a straight line in the first case, right, an axis parallel line. If we did not know whether good or bad, and we needed to have some mechanism by which we evaluate this, right. So, how do we do the evaluation? Typically is that you have what is called a test set or a validation set, right. So, this is another set of x and y pairs like we had in the training set. So, again in the test set we know what the labels are, okay. It is just that we are not showing it to the training algorithm. We know what the labels are because we need to use the correct labels to evaluate whether your training algorithm is doing good or bad, right. So, this process by which this evaluation happens is called validation, right. At the end of the validation, if you are happy with the quality of the classifier, we can keep it. If you are not happy, we go back to the training algorithm and say, hey, I am not happy with what you produced, give me something different, right. So, we have to either iterate over the algorithm again, go over the data again, try to refine the parameter estimation, or we could even think of changing some parameter values and then trying to redo the training algorithm all over again. But this is the general process, and we will see that many of the different algorithms that we look at in the course of during the course of these lectures actually follow this kind of a process, okay. So, what happens inside that green box? So, inside the training algorithm is that there will be this learning agent, right, which will take an input, right, it will produce an output y hat which it thinks is the correct output, right, but it will compare it against the actual target y that was given for the in the training, right. So, in the training you actually have a target y, so it will compare it against the target y, right, and then figure out what the error is and use the error to change the agent, right, so that it can produce the right output next time around, right. This is essentially an iterative process. So, you see the input, okay, produce an output y hat, okay, and then you take the target y, you can compare it to the y hat, figure out what is the error and use the error to change the agent again, right. And this is by and large the way most of the learning algorithms will operate, most of the classification algorithms or even regression algorithms will operate, and we will see how each of this works as we go on, right. There are many applications. I mean, this is too numerous to list. Here are a few examples. You could look at say fraud detection, right. So, you have some data where the input is a set of transactions made by a user, and then you can flag each transaction as a valid transaction or not. You could look at sentiment analysis, you know, variedly called opinion mining or buzz analysis, etc., where I give you a piece of text or a review written about a product or a movie, and then you tell me whether the whether the review is positive or whether it is negative, and what are the negative points that people are mentioning about, and so on and so forth. That is again a classification task. Or you could use it for doing churn prediction, where you are going to say whether a customer who is in the system is likely to leave your system or is going to continue using your product or using your service for a longer period of time. So, this is essentially churn. So, when a person leaves your service, you call the person a churner, and you can label whether the person is a churner or not. And I have been giving you examples from medical diagnosis all through. Apart from actually diagnosing whether a person has a disease or not, you could also use it for risk analysis in a slightly indirect way. I will talk about that when we do the algorithm for classification. So, we talked about how we are interested in learning different lines or curves that can separate different classes in supervised learning, and so these curves can be represented using different structures. And throughout the course, we will be looking at different kinds of learning mechanisms like artificial neural networks, support vector machines, decision trees, nearest neighbors, and Bayesian networks, and these are some of the popular ones, and we look at these in more detail as the course progresses. So, another supervised learning problem is the one of prediction or regression, where the output that you are going to predict is no longer a discrete value. It is not like will buy a computer, does not buy a computer, it is more of a continuous value. So, here is an example where at different times of day you have recorded the temperature. So, the input to the system is going to be the time of day, and the output from the system is going to be the temperature that was measured at a particular point at the time, right. So, you are going to get your experience or your training data is going to take this form. So, the blue points would be your inputs and the red points would be the outputs that you are expected to predict. So, note here that the outputs are continuous or real valued, right. And so, you could think of this in this toy example as points to the left being day and the points to the right being night, right. And just as in the previous case of classification, so we could try to do the simplest possible fit in this case, which would be to draw a straight line that is as close as possible to these points. So, you do see that like in the classification case, when we choose a simple solution, there are certain points at which we are making large errors, right. So, we could try to fix that and try to do something more fancy, but you could see that while the daytime temperatures are more or less fine, with the night times we seem to be doing something really off, right, because we are going off too much to the right hand side, right. Or you could do something more complex, just like in the classification case where we wanted to get that one point, right. So, we could try and fit all the temperatures that were given to us by looking at a sufficiently complex curve, and again this, as we discussed earlier, is probably not the right answer, and you are probably in this case surprisingly you are better off fitting the straight line, right. And so, these kinds of solutions where we are trying to fit the noise in the data, we are trying to make the solution predict the noise in the training data correctly, are known as overfit solutions. And one of the things that we look to avoid in machine learning is to overfit to the training data. So, we will talk about this again in due course, right. And so, what we do is typically we would like to do what is called linear regression. Some of you might have come across this under different circumstances, and the typical aim in linear regression is to say take the errors that your line is making. So, if you take an example point, let us say take an example point somewhere here, right. So, this is the actual training data that is given to you, and this is the prediction that your line is making at this point. So, this quantity is essentially the prediction error that this line is making, and so what you do is you try to find that line that has the least prediction error, right. So, you take the square of the errors that your prediction is making, and then you try to minimize the sum of the squares of the errors. So, why do we take the squares? Because the errors could be both positive and negative, and we want to make sure that you are minimizing that regardless of the sign of the error. Okay. And with sufficient data, right. So, linear regression is simple enough, you could just solve it using matrix inversions, as we will see later. But with many dimensions, right, the challenge is to avoid overfitting like we talked about earlier, and then there are many ways of avoiding this, and so I will again talk about this in detail when we look at linear regression, right. So, one point that I want to make is that linear regression is not as simple as it sounds, right. So, here is an example. So, I have two input variables x1 and x2, right, and if I try to fit a straight line with x1 and x2, I will probably end up with something like a1 x1 plus a2 x2, right, and that looks like a plane in 2 dimensions, right. But then if I just take these 2 dimensions and then transform the input. So, instead of saying just x1 and x2, if I say my input is going to look like x1 squared, x2 squared, x1, x2, and then the x1 and x2 as it was in the beginning. So, instead of looking at a 2-dimensional input, if I am going to look at a 5-dimensional input, right. So, that will, and now I am going to fit a line or a linear plane in this 5-dimensional input. So, that will be like a1 x1 squared plus a2 x2 squared plus a3 x1 x2 plus a4 x1 plus a5 x2. Now, that is no longer the equation of a line in 2 dimensions, right. So, that is the equation of a second order polynomial in 2 dimensions, right. But I could still think of this as doing linear regression, because I am only fitting a function that is going to be linear in the input variables, right. So, by choosing an appropriate transformation of the inputs, I can fit any higher order function. So, I could solve very complex problems using linear regression, and so it is not really a weak method as you would think at first glance, right. Again, we will look at this in slightly more detail in the later lectures, right. And regression or prediction can be applied in a variety of places. One popular place is in time series prediction. You could think about predicting rainfall in a certain region, or how much you are going to spend on your telephone calls. You could think of doing even classification using this. If you think of, you remember our encoding of +1 and -1 for the class labels. So, you could think of +1 and -1 as the outputs, right, and then you can fit a regression curve to that, and if the output is greater than 0, you would say it is classes +1. If the output is less than 0, you would say the class is -1. So, you could use the regression ideas to to solve the classification problem, and you could also do data reduction. So, I really do not want to give you all the millions of data points that I have in my data set, but what I would do is essentially fit a curve to that and then give you just the coefficients of the curve, right. And more often than not, that is sufficient for us to get a sense of the data, and that brings us to the next application I have listed there, which is trend analysis. So, I am not really interested, many times I am not interested in the actual values of the data, but more in the trends. So, for example, I have a solution that I am trying to measure the running times of, and I am not really interested in the actual running time, because 37 seconds to 38 seconds is not going to tell me much, but I would really like to know if the running time scales linearly or exponentially with the size of the input, right. So, those kinds of analysis again can be done using regression. And the last one here is again risk factor analysis, like we had in classification, and you can look at which are the factors that contribute most to the output. Okay. So, that brings us to the end of this module on supervised learning.